got to find moles so we can use our thermochemical equation. So I've got 3.2 kilograms. I know for every 1 kilogram, I need 1,000, or I'm going to have 1,000 grams. So we've got 3,200 grams of propane. And the molar mass of propane is 44 grams in 1 mole. So grams cancels out. And we've got something like 72.7 moles of propane. Right. Now we go to the thermochemical equation. The thermochemical equation tells us for every 1 mole of propane, we're going to release 2,000 kilojoules of energy. So, all right, I've got 72.7 moles of propane, and for every 1 mole, right, we're going to release 2,220 kilojoules of energy. So we're going to multiply. Right, to get a giant number here, let's see, times 2,220. Let's see, 2 significant figures, because 3.2 kilograms of propane is 2 significant figures. So I would say something like 1.5 times 10 to the 5 kilojoules of energy would be released. If you want to say a negative, right, we're kind of already implying that it's negative because we're saying it's energy released, but yeah, a negative 1.6 times 10 to the 5 kilojoules of energy. Mass to moles, and then once we had moles, thermochemical equation is going to give us moles to energy for that reaction. So any question? Yeah. Yeah, correct. Like if this had been for like oxygen, for example, if we had mass of oxygen in the reaction, we would have gone and said, okay, for every 5 moles of oxygen, this is the energy released. Exactly. So we only had 1 mole of methane, so I only needed 1 mole down here, because that's what we were working with. But certainly if it was oxygen or carbon dioxide or water, we would change that molar coefficient, because yeah, the energy would be different per mole. Right now it's, per 1 mole of this, that's the energy. For 5 moles of this, that's the energy. Yep. Any other questions on that? All right. So we'll jump to module 9.